Alright, so let's dive into something called a divide and conquer algorithm. So it's a clever way to tackle big problems by breaking them into smaller parts, solving those parts, and then bringing everything back together for a final solution. Here is how it works. First, we take our big problem and slice it into smaller, more manageable pieces. We call these as subproblems. So next, we put on our problem solving hats and tackle those subproblems one by one. We solve them independently, like solving a puzzle piece by piece. Now comes the magic part. So we take the solutions we found for each subproblem and combine them in a clever way to get the solution for the original big problem. And guess what? Recursion is our trusty sidekick in this process. So it's like having a friend who knows how to solve the small parts and can teach us how to put everything together in the end. So when you encounter a tough problem like this that seems too big to handle, remember this divide and conquer strategy. Break it down, solve it bit by bit, and with a dash of recursion, you will be on your way to conquering it all. Alright, let's take a closer look at how these divide and conquer algorithms actually work. Think of it like following a recipe to solve complex problems. Step 1. Divide. Imagine you have a big problem that's like a puzzle with many pieces. In this step, we slice that big problem into smaller, more manageable parts. We do this using recursion, which is like breaking down the puzzle into smaller and smaller pieces. Step 2 is conquer. Now that we have these smaller puzzle pieces, we need to solve them. If a puzzle piece is small enough, we can solve it directly. But if it's still too big, guess what? We use the same recipe again. Yeah, that's right. We apply the same divide and conquer strategy to these subproblems as well. Step 3. Combine. Here comes the exciting part. Once we have solved all these smaller puzzles pieces, we put them back together in a smart way. It's like putting this puzzle back together. But this time we know exactly where each piece goes because we solved them individually. Now, let's practice this recipe with an example. Sorting an array using the merge sort approach. Imagine we have an array with these numbers 7, 6, 1, 5, 4 and last we have 3. First, we divide the array into halves and keep dividing until we have single element. Then we start solving these small pieces, which is our conquer step. We sort these individual elements. At the same time, we are also combining them back into a sorted order. So, as you can see, with the divide and conquer approach, we break down a big problem into smaller ones, solve them, and then bring everything together for the final solution. It's like solving a puzzle piece by piece, and when we are done, we have conquered that big problem. Let's delve into understanding how we measure the complexity of these divide and conquer algorithms. Think of it like measuring the time it takes to solve a problem using a specific recipe. We use something called the master theorem to calculate the complexity of a divide and conquer algorithm. The theorem helps us figure out how long it will take to solve a problem based on a few key factors. Imagine you are baking a cake using a recipe. The recipe might look like this. The time function t of n equals a times t of n over b plus f of n. Here is what each part means. T of n is the time it takes to solve a problem of size n. A is the number of smaller subproblems we divide the big problem into. N over b is the size of each subproblem. we assume all subproblems are the same size. F of n is the extra work we do outside of solving subproblems. It includes things like dividing the problem and putting the solutions together. Now, let's apply this to an example, the merge sort algorithm. For merge sort, our equation looks like this. The time function t of n equals to 2 times t of n over 2 plus big O of n. Here is what's going on. We split a problem into two subproblems each time. So A equals to 2. The size of each subproblem is half the original. So n over b equals to n over 2. The work we do to combine the subproblem is big O of n. By putting these values into the master theorem, we can figure out the time complexity. In this case, it's approximately big O of n log n. Think of this complexity like the time it takes to bake a cake. The larger the cake, the longer it takes to bake. So in summary, the master theorem helps us predict how long a divide and conquer algorithm will take to solve a problem based on these key ingredients. It's like using a recipe to estimate how long it will take to bake the cake. Divide and conquer versus dynamic approach. So, in the divide and conquer method, we take a big problem and break it into smaller pieces. We then solve each small pieces separately. But here's the twist. We don't save the answers to those smaller pieces for later. It's like solving a puzzle but throwing away the solved parts when we are done. On the other hand, in dynamic programming, we solve those smaller pieces as well, just like in divide and conquer. But here is the cool part. We do keep those answers handy. We save them in a special memory so we can use them later. It's like solving the puzzle and keeping the solved pieces in a box for reference. So, when do we use each strategy? Well, imagine you are solving a puzzle and some pieces appear in the puzzle multiple times. If you don't mind solving the same pieces over and over, go with the divide and conquer approach. But if you want to save time and not repeating yourself, dynamic programming is the way to go. Here is an example to make it crystal clear. Think about finding the Fibonacci series. You know those numbers that add up in a special way? The fib function calculates the Fibonacci number for the given input n. If n is less than 2, it returns 1. Otherwise, it recursively calculates the Fibonacci number for n minus 1 and n minus 2 and add them together. With the divide and conquer approach, we use a simple rule to get each number. We don't remember the numbers we have already figured out. The fib function uses dynamic programming with memorization to calculate the Fibonacci number for the given input n. It checks if the result for n is already stored in the mem list. If so, it returns the stored value. Otherwise, it calculates the Fibonacci number using recursion, stores the result in mem, and returns the calculated value. So, this approach helps avoiding redundant calculations by storing and reusing previously computed results. So, with dynamic programming, we use that same rule, but we are smarter about it. We remember the numbers we have already found and keep them in a memory box. This way, when we need a number again, we don't have to work it all out over again. We just grab it from our memory box. So, whether you are tackling a puzzle or crunching numbers like the Fibonacci series, choose the strategy that fits the situation. Sometimes it's about quick fixes and other times it's all about long game and efficiency. Alright, let's talk about the cool advantages of using the divide and conquer method to solve problems. Imagine you are facing some tough challenges and you want to solve them like a pro. And that's where divide and conquer comes into picture. One awesome advantage is that it can speed up things, especially when dealing with big numbers. So let's say you are multiplying two matrices and you are using a normal method. It would take you a lot of calculations, and that's like doing maths for hours. But if you switch to the divide and conquer approach, things get faster. With a method called Strasson's matrix multiplication, you can do those calculations in a more efficient way. It's like using a smarter tool for the job. And guess what? The time it takes to solve gets shorter, almost like magic. The complexity drops from being cubed to a special number that's around 2.8 or 74 times the input size. But that's not all, right? Divide and conquer is like a superhero when it comes to solving problems in computers that have more than one brain. We call them processors. It's like dividing the work between your friends, so everything gets done faster. Oh, and it's a clever way of using memory, right? You know how sometimes you need to go to your room to get your toys. Well, divide and conquer is like keeping all your toys close by, so you don't have to run back and forth. It saves time and energy. So, if you want to be a problem solving champ, divide and conquer is your trusty sidekick. It makes tough problems easy, speeding things up, and even work great with computer friends. It's like having a smarter strategy to win your battles against tricky problems. Let's talk about some real world applications of the divide and conquer strategy. This approach is like breaking down a big problem into smaller, manageable parts. Here are some examples of where we use it. Binary search. Imagine you have a huge sorted list and you want to find a specific number in it. Instead of checking each number one by one, you can keep dividing the list in half and quickly figure out where that number is. Merge sort. When we want to sort a long list of things, we can divide it into smaller lists, sort those, and then merge them back together. This often turns out to be more faster than trying to sort the whole list at once. Quick sort. Similar to merge sort, but with a slight different approach. You pick a pivot element and then you divide the list into parts small and bigger than the pivot. You sort those parts and put them together. Strasson's matrix multiplication. If you have two big matrices that you need to multiply, the traditional way can take a lot of time. But using the divide and conquer method, you can split the matrices into smaller ones and do the math for efficiently. Karatsuba algorithm. This is a clever way to multiply really large numbers. Instead of doing the usual multiplication step by step, you break the numbers into parts and do some smart calculations to get the result. So, divide and conquer is like a problem solving superhero that helps us tackling big problems by breaking them into smaller pieces and then conquering them one by one.